Okay, in our discussion of perfect square trinomials and difference of squares, I kind of threw a fastball at you in terms of, or a curveball if you would, by introducing you indirectly to polynomials of several variables. So usually our polynomials up to this point have just had an x in it. Sometimes they have a y or an a or whatever, but there's only one variable. But now we're going to take a look at in 4.7 what happens when I have a polynomial that has more than one variable in it, several variables. So there's our difference of square models. So you can see it's a polynomial, right, with two variables. Here's a perfect square trinomial and another perfect square trinomial, and both of them have more than two variables. So in 4.7, we're going to basically take a deeper look at these types of polynomials. The good news is all the polynomial lingo that we've learned up to this point still holds true. Everything is still the same. So you're looking at a monomial here, right? This piece, the -3, represents the coefficient. These are the degrees of the exponents. Everything still remains true, right? So this is a trinomial down here. So all the language remains the same. However, there is one thing that has to change because of the fact that we have two variable parts risen to a power. So the only thing that's going to change is the degree of a term. And this is how it's going to change. Under normal circumstances, as we saw in, I believe, 4.1 and 4.2, the bases are different here, so we are not supposed to add the exponents. However, if we think for a moment that we're going to evaluate this, if we let x equal to y, then this expression, right, oops, made a boo-boo, this expression becomes that. And then now the base is the same, and so we can actually add them. So in order to determine the degree, right, what's the power that we're raising to, we open ourselves to the possibility that x might be y. So therefore the highest power that will ever be between these two would be 5. All right, and so under normal circumstances, we usually don't do that. But when you are trying to find the degree of a term with several variables in it, that's when it's okay. So this is a degree 5 term. Everything else remains the same. The concept of descending order, the concept of the degree of a polynomial being the highest degree term, and then the lead coefficient out in front. Monomials, trinomials, everything remains the same. So let's go put this in action, right? I've got 3 different polynomials of several variables, and let's first go through and determine the degree of every single term. So this would be a degree 7, right? 5 plus 2 is 7. Again, we normally don't add them up, but in determining the degree of the term, we do. Here, the degree of this term is 5. 3 and 2 is 5. The degree of this term is 6, and then the degree of this term is 3. And so when you are trying to determine the degree on a term with several variables, that's when we are allowed to add up the exponents. And again, under any other area in math, you don't do that. Going along, this term obviously is a degree 2 term, right? That kind of fits our old definition. Here is a degree 3 term. This would be a degree 6 term, and this would also be a degree 2 term. All right, so the degree of a term, right? It's the power, or if we have several variables, we sum up those powers to get the total degree. Last but not least, this is degree 2 term. Right here, this is the first power, that's the first power. So this is also a degree 2 term, and then that's also a degree 2 term. All right, so degree of term, there's the one item that's going to change. Descending order, well, what that means is we basically reorder our polynomial from highest degree term to lowest. So if you take a look at my first example here, right, I have a degree 7 and then a 5, a 6, and a 3. So this is not in descending order. So rewriting it in descending order, we get 3x squared y to the 5th. Minus 5x squared y to the 4th, minus 4x cubed y squared, and then plus an xy squared. So degree 7, 6, 5, and 2, we are now in descending order. All right, if we take a look at the next one, it's definitely not in descending order, right? There's our degree 6 term, and it's not out in front. So rewriting this, we get a negative x cubed y cubed. The next highest one would be a positive 5xy squared. And then we have a choice, all right? We have a 2 degree 2 terms, so one really doesn't supersede the other, but usually what takes over now is your alphabetical order. X comes before y. So we'll reorder it that way. Although technically, if you don't want to use alphabetical order, they're the same order of precedence, all right? So there would be that polynomial descending order, degree 6, degree 3, degree 2, degree 2, descending order. And then 3 is interesting because all the degrees, right, every single term has degree 2. So really, in descending order doesn't make a whole lot of sense here because everything is the same and you can rearrange it any way you want. But it's pretty common practice. I want you guys to kind of notice something. If we think alphabetically order-wise, when I have things that are of the same, notice we go by alphabetical order, and then notice that in terms of the x, it is in descending order, right? In terms of x, this is degree 2, degree 1, and then degree 0. And then as we descend in x, we are ascending in y, right? So there is no y, so degree 0 in terms of y, degree 1 in terms of y, and then degree 2 in terms of y. So this is one way that mathematicians, even though there's really technically not a descending order, to organize our terms, we usually go descending order in one term, and then ascending order in the other. And that's what typically happens. You'll even notice back here, that's what happened here, right? There's an a squared, a to the first, and then no a. In terms of b, there's no b, b to the first, and b squared. So I was kind of sneaking that at you at the very beginning, right? And so here again, degree 2, degree 1, degree 0 in terms of a degree 0, degree 1, and degree 2 in terms of b. So that idea that when everything is the same degree, we basically go in descending order. And then last but not least, even here, right? A comes before b, so that term in front of that term. So that's how we basically do that. So there's your descending order. The degree of the polynomial, well again under definition, the degree of the polynomial is the highest degree. So for this poly, right, this is a degree 7 polynomial because it's the highest degree. This would be a degree 6 polynomial because the highest degree is 6. And of course this one would be a degree 2 polynomial because everybody is to the second power, all right, or has a degree 2. So there's my degree of a polynomial. Again, it's still the highest degree that we have available. And then of course the leading coefficient, as we mentioned, the lead coefficient goes with the term that's determining the degree of the polynomial, the highest power. So the lead coefficient in this case would be 3. The lead coefficient right here would actually be -1. And then right here, again, for what I have, the lead coefficient is technically 4. But we could rearrange this and rewrite it in terms of y. But let's just kind of stay with our standard operating procedure, alphabetical order, descending order in one, ascending in the other. So I would basically say our leading coefficient is 4. Okay, so there's an introduction to the language, what a polynomial several variable looks like. The polynomial lingo stays the same, with the exception of a degree of term. We have to rethink it. We determine it by adding the powers, even though we wouldn't do that in normal algebraic circumstances. And then, of course, you're basically using the lingo, degree of terms, degree of descending order, degree of polynomial, leading coefficient. So next up, item for bit, now that we know these, how do we add them, subtract them, multiply them? And that's coming up in the next videos. See you guys then.